thanks to the SOC for giving me this opportunity to present these results, which are about planet architecture and the connection with stellar metallicity. That's good that in the previous two talks you heard a bit about the models of planet formation, so I don't need to describe it, the models. You saw this one of these figures that giant planet formation depends on stellar metallicity. That this is what the observation shows. So it seems it's easier to form a giant planet when you have in the disk you have more metals than if you have a lack of metals. Still, there is a problem to understand which is the functional form of this correlation, but the correlation is apparent, and this correlation was found almost from after the first few exoplanets were detected. And as it was mentioned before, seems there is no correlation with metallicity for small planets. In these two plots, and in the first plot, you can see that the metallicity distribution of planets with with small radius, smaller than 4 of that of the Earth, you can see that the metallicity distribution is much wider than for the giants. So this means that small planets can form around many metal-poor stars, metal-rich stars. So it seems that formation is independent on the disk metallicity. But I would refer you to see this last paper of Wang and Fisher, 2015, where they show that even seems that the small planet formation is a function of metallicity, even for planets which have a radii below 2 to the Earth radius. So if there is if planet formation depends on the metallicity, it's logical to think that maybe it should have a metallicity of the disk should also affect kind of the orbital properties of the planets. In this work, Dawson and Rickley, they found that if you look at the planets, giant planets, in the distance from 0.1 to 1 AU, they found that planets around metal-poor stars have lower eccentricities, smaller eccentricities compared to those which are around metal-rich stars. So what they found is that eccentricities of giant planets in these regimes from 0.1 to 1 AU are larger, the eccentricity distribution. And this is the schematic explanation of what they found. The main idea is that in metal-poor systems, in metal-rich system, it's easier to form giant planets, as it was shown before. So you have more planets, and the planet-planet interaction will increase the eccentricity distribution. And in the metal-poor system, you don't have many planets, and you have only smooth disk migration, which means that the eccentricity should be smaller. However, there is another explanation for what was found. The recent paper by Zhang, Turner, and Cumming, they showed that only the disk interaction, you don't need to have many planets in the system to have the eccentricity, to have an increased eccentricity around metal-rich stars. From this 0.1 to 1 AU regime, depending on the metallicity of the system, you have a gap or you don't have the gap, which is responsible for the damping or not increasing eccentricity. Another interesting results related to metallicity and orbital properties of planet was found in Bouget and Nesvorny in 2013. These authors used the Kepler data, the planet candidates. These are not confirmed planets, these are not confirmed planets. What they found is that if you look at the planets with radii smaller than 4 of the Earth, they found that there is a lack of planets with very short periods, smaller than 5 days, around metal-poor stars. And the same, if you look at Neptune-like planets, in fact, they didn't find any Neptune-like planets around metal-poor stars. So their main conclusion was that small planets around metal-poor stars don't migrate much. They don't migrate much closer to their suns, and that's why we cannot see them. So they didn't speak about which kind of type of migration is that, but it's probably they were speaking about disk migration. And what is interesting in this plot that they didn't find any correlation for giant planets above 0.3 Jupiter mass. And since in Porto we are hosting one of, well, I would say the best catalog for planet host stars, which is really very homogeneous. And for radial velocity detected planets, we have 90%, we analyzed 90% of the hosts in a homogeneous way. And we decided to see if really the metallicity affects the planet, metallicity correlates with the period of the planets in the high mass regime. And in this study, we removed the evolved stars because they show different metallicity distribution, and we also excluded the transit hosts because the detection methods are different and detection biases are different. So what they found, you can see in this plot that the red points are the planets around metal-poor stars. We found that in most of the cases, giant planets around metal-poor stars have longer periods. So there could be two explanations for that. Either planets in metal-poor system form farther from their hosts, or they migrate less. And in the paper, we also show that probably since there are we don't have giant planets with short periods, smaller than 100 days, probably this migration is less rapid than it was assumed in the previous works. And when we looked closer to the small planets, Earth-like planets, we found kind of similar to what Bouget and Nesvorny were found, but it's a bit different. In their study, they found that planets around metal-poor stars don't have short periods. We found short-period metal-poor planets, but we didn't find long-period metal-rich planets. They are kind of similar, but they are also different. We still don't know if there is a detection bias or not. But if there is no detection bias, this would mean that all the metal-rich planets in the metal-rich system, they all migrate because they have always shorter periods. And in the bottom plot, I showed the planets which in the system which have the longest period. So we are sure that there is no higher mass planet in this system which push them to go to this close. So these are the longest period planets in this system. And you can see in the blue the habitable zone, assuming that the host is the sun-like star. So it's more or less from 300 days, the period from 300 days to 700 days. And if we find the planets in the habitable zone, and if we extrapolate our result, we could think that probably these planets around inhabitable zone should be found around metal-poor systems, because in most of the cases, planets in the metal-rich system, they migrate. And when we wrote the paper, at that time, we were thinking that all these results can be well explained with the Core-Accretion. Well, can be only explained with the Core-Accretion model. But recently, like a few weeks ago, there was this paper by Nayakshin where they assumed a gravitational instability model at the beginning to form this at the beginning of the formation, and then they added the pebble accretion and the migration as we see in the Core-Accretion model, and they found very similar picture to what we observed. That the planets at least for the giant gas giants, they found that mostly the planets with around metal-rich system have metal-poor system, they have longer periods. So it seems that both models, Core-Accretion model and gravitational instability, modified gravitational instability model, can explain this. And when we had this good catalog of planet hosts, as a byproduct result, we've also studied the eccentricity distribution of giant planets. And what we found is that giant planets, very massive giant planets with a mass above 4 Jupiter mass, show systematically longer eccentricities. And this is true for single system and multiple systems. So this is not because of the planet-planet interaction. This is most probably because of the planet-disk interaction. And Same this goes in line with the simulation, and just this planet-disk interaction can change the eccentricities. And we also found that the giant planet, very massive giant planets with smaller eccentricity have also shorter periods. It's difficult to explain why, but this is the result. So these are most what I wanted to say. Just metallicity is very important, not only for planet formation, but also for the shaping the orbital properties of planets. And in previous times, sorry, I did a mistake. I was saying that heavy metal rules, but then I realized that heavy metals rule. There was a mistake of writing. Thanks.